Okay, now let's just take the matrix. This, which I think is a non-singular matrix. Okay? We calculate the determinant and verify that. Okay? So, I'm going to do this using this elementary matrix. In other words, I'm just switching the first and second row. Okay? And E1 is its own inverse. Okay? And then E2 is going to be this matrix, where I'm just adding -2 times the first row to the second. It's going to give me 1, 2, 3, 0, 5, 0, -1, -7, and 3, 4, 2. Check my arithmetic. Okay? So I've got my 0 here. I need a 0 here. Okay? So that's going to be easy. E3. Add -3 times the first row to the third. It's going to give me a 0 here. And if I do the arithmetic correctly, I've almost got upper triangular form here. Okay, so I'm going to have a 0. -3 times 2 is -6. Added to 4 is -2. -3 times 3 is -9. Added to 2 is -7. Okay? And then I'm not going to continue by trying to make this 1, but I am going to make this 0, and that'll give me an upper triangular matrix. And we know that the determinant of an upper triangular matrix, you might not know it yet, Mark, since you had the sleep incident last night, but it's very easy to see that the determinant of an upper triangular matrix is just the product of the numbers you end up with in the diagonal. Part of the assignment, when you do it, you'll see it, and it's really easy. Right? Very obvious. Actually, maybe you did that, because I think that was in what I already looked at.
Yes.
Yeah, the
I haven't
upper triangle
looked at
or
it,
lower
what I
triangle
assigned
with
last time.
any that
Yeah,
straight.
so you've got it. So you both got that, so that's something that you simply know. So, all I have to do then is add -2 times this row to this, and I'm going to get a 0 here, right? So it's going to be 1, 0, 0, 0, 1, 0, 0, -2, 1. And that's going to give me 1, 2, 3, 0, -1, -7, 0, 0, and -2 times -7 is +7. Is plus 14, added to -7 gives me 7, right? Okay? Now, uh-oh, I kind of screwed up. Shouldn't have done that. Anyhow, this is my matrix A. Okay? Now,
The second
I
row
really
in
shouldn't have
E1.
used a matrix. All these matrices are lower triangular. This one isn't. I think I was going to screw things up. So I kind of screwed up. So I did that on purpose, just so you would understand that you can screw it up if you're not careful. Believe me? No, okay, I'm reducing the matrix. I want to make this one first, okay? I can fudge on this, and I will in a minute, by saying, okay, this is my original matrix, I didn't mean this one, and now here's my E1, my E2, and my E3, right? I can do that, and I will, okay? But this helps just to show one of the things you have to be careful of. I think you can't reverse rows. I'm not sure. Let's work it out and see if we can prove it. Okay? Can't switch rows. So what we have is, this is upper triangular matrix. We're going to call this U for upper triangular. Okay? So I can say that U equals E4, E3, E2, E1 times A. Okay? So A is this. Okay? And that should equal L U. So our goal is for L to be lower triangular, U to be upper triangular. So like the determinant of A is just going to be the product of the diagonals of the lower triangular with the product of the diagonals of the upper triangular. Okay? That's a lot of trouble to go to get the determinant, but there are other important things you can do with the LU decomposition. Okay? It's a simple decomposition that makes it easier to deal with the matrix, except I think it's not going to work, because I think when I do these inverses, which I'm going to do, this is going to screw it up. Okay? Because it's going to take the lower triangular that I get from these inverses and put something above the diagonal. Okay? In other words, the second row, second column element is going to end up in the first row. So it's not going to be lower triangular. So anyhow, the inverses are, so let's do E1. Yeah, E1 inverse is 0, 1, 0, 1, 0, 1, 0, 0, 1. E2 inverse is this, and you know how to do inverses. You know, I mean, your homework is pretty good with the inverses of elementary matrices. I'm not going to explain it again. I'm just going to write it down, and you catch me if I do something wrong. Okay? And then this one, which is going to be getting smaller and smaller, so I get them all in it. Well, that's going to be pretty narrow. 0, 1, 0, 3, 0, 1, and then 1, 0, 0, 0, 1, 0.
I'm curious about something.
0, 2, 1.
Wouldn't the E1 be that the first one be, well, the first one is where the the second one goes where the first one is, and the new second one would be the first and second added together for your E1? I'm curious.
E1 just switches the first and second rows, right? So how do you get it back to where you were?
Well,
You switch the first and second rows again.
I get that. What I mean is, where's the, for the second line, the 101? What is it?
It shouldn't be 101, it should be 100. Just thinking ahead to right in the third row, and it's right in the second. Yes, thank you. That's what I said. Catch me if I do something stupid. Okay? Or careless, which is kind of the same thing. Okay? So this equals what? Well, I'm going to leave this one alone and hopefully write it out correctly this time. And then I'll multiply these two together. So this gives me 1, 0, 0. And I get 0, 1, 0. Wait a minute, I'm careless. Okay, that's going to pick out the second one, and that is going to be 3 times the first one plus the second one, which is going to give me 3, 0, 6. 3, 0, 1. That can't be right. 3, 0, 1 times this gives me the 3. 3, 0, 1 times this gives me 2, not 0. Okay? I got it right? Okay? So we'll notice that this is still lower triangular, right? And it's easy to prove that if you got 2 lower triangular matrices, the product's going to be lower triangular. Probably put that on homework. Okay? Okay, so then we're going to multiply by this. We're going to pick out the first row. Second row is going to give me 2, 1, 0. And then third row is going to give me 3, 2, 1. And I didn't write out my matrix that I wish I hadn't put in there in the first place. So I'm going to have to multiply it again because they don't trust me to remember what I just did. But it's going to be 0, 1, 0, 1, 0, 0, 0, 0, 1. Multiplied by 1, 0, 0. Make sure I'm looking at it right. And something wrong. Because I'm looking, I don't know. I multiplied this by this, so let me fix that. Been reading articles on how the brain handles perception, what it suppresses and what it attends to. And my brain suppressed what I should have been looking at. Okay, so let me do it again. It gives me 1, 0, 0. It gives me 2, 1, 0. And that gives me 3, 2, 1. Okay? And now it gets screwed up. But so far, you know, this much is lower times upper, right? And then when we do this, just to see what happens and why it happens, we get the 2, 1, 0 up here. It's no longer lower because of that 1. Okay? And then we get we get the 1, 0, 0, and we get the 3, 2, 1. Okay? Which just, again, switches these 2 rows. Okay? So what we want, just to illustrate the process, is now call this matrix B, okay? And call this my yellow E1, my yellow E2, and my yellow E3, okay? And we can then say that B equals yellow E1 inverse, yellow E2 inverse, yellow E3 inverse, times U, and this is also yellow U, okay? That's my yellow U. Okay, same as the other. Because obviously if we start with B, then we don't have this one anymore, and then we have these three matrices. And hopefully that's not too confusing, okay? And then E1 inverse, E2 inverse, E3 inverse will be my former E2 inverse, E3 inverse, E4 inverse, which I did here, before I multiplied by my bogus E1 inverse, my bad decision E1 inverse, okay? I didn't want to have fractions, so I had to put the 1 up there. Should have started with it, okay. So it gets more complicated if you have fractions, but it's still, the process is simple, it's just a little more tedious. So we get this, okay? And that equals LU. This is lower, this is upper. And if you avoid switching rows when you reduce your matrix, it'll work out that way. Always lower times upper. Okay? So that's pretty straightforward. But now, okay, one thing we can easily do is determine it. Okay? And that's not particularly important. We wouldn't go to all that trouble to calculate the determinant. Probably wouldn't. Maybe with a big matrix we would think about it. But the determinant should equal a B, should be determinant of L times the determinant of U. Because the determinant of LU is the determinant of L times the determinant of U.
So like -7?
Sorry?
So like -7?
Yeah, that's determinant of U. The determinant of L is 1. Hadn't gotten that far, but it's obvious. Okay? Now you can actually do the determinant of V. Okay? And verify. Let's see, it's 1, and that's going to be 6, 10. We're going to have a 10. Then we're going to have -2 times 4 and 6, which is 10, so it's now -10. So this one had better have a determinant of -1. 2 times 4 is 8. 3 times 3 is -9 times 3 is -3. So we had -10. We had 10, and then we had -10. Now we got -7. Wait a minute, that's -3. I guess we said -10, then we had 10. No, we don't. Well, anyhow, you do it, and hopefully it works. Okay? Kind of looks to me like it's going to come out -7, but I'm not sure about the sign anymore. Too much, too much. Okay? Maybe that was an instance of selective perception, but it was just incidents of tired neurons. Okay? Decaying synapses. So it should work out. You can verify it. No reason it shouldn't, if it was done right. Okay. Now, another thing we can do is we can use this to solve a matrix equation. Okay? So, let's do that.